everybody's filing in, I'll talk a little bit very briefly about tomorrow. Here's a map of Carmel and Point Lobos. Got
wow. Do you want to put it up?
I can't. These will be available tomorrow. You can take one. Let's see. So the lecture tomorrow morning is at 9, not 9:30. The buses will leave at 10 plus epsilon. It's possible that it will be foggy and cold in the morning. It will probably be cool in the evening, so you might want to bring something to keep you warm. We'll end up in Carmel around lunchtime. You could bring a lunch. You could buy lunch there and take it to the beach. You could buy lunch in a restaurant. There are a variety of options. As it happens, there's an antique car show going on in Pebble Beach, so Carmel will probably be moderately crowded and interesting tomorrow. In fact, all the mathematicians will be lost amongst the car buffs. The plan is to spend a couple hours in Carmel, meet the buses, go to Point Lobos, spend a couple hours there, then have the buses drop us in Monterey, probably between 5 and 6, so we can get into the aquarium at 7. There's fish watching and hors d'oeuvres from 7 to 8, dinner at 8. We think we'll get on the bus between 9 and 9:30, and we think we'll get back here between 11 and 11:30. The buses will stop down the hill. What the contract says is at quote-unquote various hotels. So one bus will certainly also come back up here for people who left cars here. Are there any questions? Anything I'm forgetting about tomorrow?
Is there room for other persons?
Significant others, yes. If you signed up, the significant others or signed up are all in. Any other questions? The chair doesn't want to get up. He has nothing new to say about Professor Lenstra.
Well, it so happens I have nothing new to say either. This is a tutorial on lattices consisting of 2 parts of 1 hour each with an intermission in Monterey. I have 2 main messages. One is that I intend to explain what is known as the lattice-based reduction algorithm, or the LLL algorithm. But more importantly, I try to explain how you use this algorithm and how you recognize situations in which lattices are useful and how you construct those useful lattices. So let me begin with the definition of a lattice. That is actually one of the attractive features of the subject. You can plunge right into the middle of it. There's absolutely no depth. All you need to know, you learned already by teaching linear algebra from Anton. You need to know what a Euclidean vector space is. And a Euclidean vector space, that is a finite dimensional vector space over the field R of real numbers, equipped with a symmetric bilinear form of which the diagonal is positive definite. And the only thing that I have to say about Euclidean vector spaces is that I will always take it for granted that these Euclidean vector spaces come with a metric. The inner product of a vector with itself is at the same time the square of the distance of that vector from the origin, and in general the distance between 2 vectors in a Euclidean vector space is the distance from their difference to 0. So that is what I mean by a Euclidean vector space. It has a metric. It has, of course, as a consequence, a topology. What I mean by a lattice is a discrete subgroup of a Euclidean vector space, where discrete just means that there is an open neighborhood of the origin that intersects the subgroup only in the 0 element. If I say subgroup, clearly what I mean is an additive subgroup. So the type of thing that you have to think of is drawn here, artistic impression of a lattice in a 2-dimensional vector space. The picture is always intended to imply that the quadratic form is the usual one, where the distance is proportional to what you actually measure with a measuring tape. Okay. The first important numerical invariant that we attach to a lattice, and that gives at the same time an alternative description of what a lattice is its rank. It is an easy theorem, which I will not prove for you, that if I have a subgroup of a Euclidean vector space, and for my Euclidean vector space, I will often take the Rm for some non-negative integer m with a standard quadratic form, some xi square being the square length of a vector x. A subgroup of Rm is a lattice if and only if it has a basis over Z, so B1 through Bn is supposed spans L over Z, Z being the integers, that is at the same time linearly independent over the reals. So for example, if you just take a one-dimensional vector space like R itself, you should not take two vectors like 1 and square root 2, which are not linearly independent over R, even though they are over Z. In particular, we see from this that is n is at most m. I will refer to such a set of vectors as a basis of the lattice, or equivalently a basis of the lattice over the integers, not to be confused with a basis of the vector space. And the rank, which depends only on the abelian group structure of my lattice, is defined to be the number of vectors that you need. That is the dimension of the span of L, so that is independent of the choice of the basis. I have here an alternative definition of a lattice, which I only show in order to emphasize what I consider important about a lattice. And what I consider important about a lattice is, first of all, the L itself, and secondly, the inner product, or if you like, the quadratic form that you get from the Euclidean space. The Euclidean space itself is only there to help us and to spark our imagination. But you can also give a definition of lattices purely in terms of L and this real valued function Q on L, which you have to think of as being the square length of your vector. Namely, the definition consists of four conditions on the pair L, Q. First of all, L should, as an abelian group, be finitely generated. I also write it in an additive manner. Secondly, there is an equality in algebraic identity for this Q, which is known as the parallelogram law. If you take a parallelogram in the plane and two of the sides are x and y, say, then this says that the sum of the squared lengths of the four sides of the parallelogram is the sum of the squared lengths of the diagonals of the parallelogram, a well-known property of Euclidean vector spaces. Also, I have that non-zero vectors will have non-zero distance to 0, and every big sphere in my Euclidean vector space, every large ball, contains only a finite number of lattice elements. And you can show that conversely, these four conditions imply that you can construct a Euclidean vector space actually just by tensoring your lattice with the real numbers and by using your Q to get a Euclidean structure on that vector space. You have to prove a few things there, but that is not difficult at all. I also should point out that I am not requiring Q of Z to be positive here. That is a consequence of these axioms. Okay. Let me give you a few examples of lattices as they occur in number theory in a perfectly natural manner. The first is that I take an algebraic number field, that is to say, a field that contains the field of rational numbers and that is of finite degree over the rational numbers. And then I take for L a finitely generated additive subgroup, and there are many additive subgroups of a number field to which you want to apply this in practice. For example, the ring of integers, or certain ideals in the ring of integers, or subrings or fractional ideals. There are many such L's that you can think of. And what is important to keep in mind is that in such a situation, such an L always comes with a perfectly canonical and natural Euclidean structure, this map Q. Namely, you take for Q of x the sum of the squared absolute values of the images of x under the several embeddings of my field K into the complex numbers. Even though you are taking a function here that looks sort of symmetric, you should keep in mind that it is in general not the case that this Q is rational valued, although it is for several important classes of number fields. But these are usually true real numbers, not just rationals. And that implies that applies to an even greater degree to my second example, where I start from the same notation, but now I pass to a multiplicative group. I take Z sub k to be the ring of algebraic integers in K. I look at its unit group, Zk star. It has a finite subgroup. The group of roots of unity in K contains, for example, -1. I factor it out, and then I get a lattice, a finitely generated abelian group with a perfectly natural function Q, defined on it, again, a sum over embeddings, but now we take logarithms of absolute values before we start squaring. In this formula, U bar is supposed to be the coset of a unit modulo this subgroup mu that I am factoring out. And as a third example, group of points on an elliptic curve. I take an elliptic curve as defined yesterday in the lecture of Björn Poonen. So I take 5 rational coefficients, A1 through A6, omitting A5, with a certain non-vanishing condition on the discriminant. We know that E of Q, the set of rational projective solutions to this equation, forms an abelian group. It has a torsion subgroup, EQ sub tor. I can divide it out. That gives me a finitely generated abelian group. And again, it comes naturally equipped with a function Q that satisfies all of my axioms. And this function Q is basically obtained by taking a point P. Well, the bar, again, just indicates the fact that I am dividing out by this finite subgroup. If I take a point P and I write it in projective coordinates, x, y, z, then I can normalize my x, y, z. They are in principle rational numbers, not all of them 0, by first of all removing a common denominator so that they are integers, and secondly by removing a greatest common divisor so that those integers have no common divisor. That makes x, y, and z uniquely determined by the point up to sign. And once you write the point in that manner, you take the absolute value, that is good to get rid of the sign, you take the maximum, and you take the logarithm. And that is supposed to be the Q of a point, except that now all my laws, especially the algebraic rule, the parallelogram law, is only valid with a certain error. In order to get rid of this error, you pass to a limit so that you do get a true lattice. Okay, so this is a set of examples that I really only wrote down to illustrate that these lattices occur in number theory in a perfectly natural way. However, they are by no means the primary examples to which one wants to apply the LLL reduction, lattice-based reduction algorithm. And the reason why this is true, there are several reasons, but the main reason is that if you look at the 2 most interesting lattices that I wrote down here, first of all, the unit group, and secondly, the Mordell-Weil group, the group of rational points on an elliptic curve, then the main questions people in algorithmic number theory ask about those lattices is find a basis for them, finding a basis for the rational points or a set of independent generating units. And that is exactly what in the context of the lattice basis reduction algorithm we take already for granted. In the lattice basis reduction algorithm, we give ourselves a lattice. We have to make clear to the computer which lattice we are talking about. In particular, we want to know already what the rank is, which is not so clear in this case. And I will in a minute say more about how I specify such a lattice, but certainly I need to know a basis already. In this situation, the situation of subgroups of rings of integers, it is in most practical cases not so difficult to write down a basis, and in this case it is usually still quite useful to apply lattice basis reduction algorithms, but I will have nothing further to say about this example. There is another complication that we face if we want to explain to our computer which lattice we are talking about, and that is that in all three of the examples that I have shown here, the range of values of Q is essentially really the real numbers. There is no good reason for any of those to be rational. And that means that if we want to specify those real numbers to our computer, we run into the problem of precision. And that is, again, a problem that I do not want to discuss in these lectures. So what I would like to start with now is how do we make clear to our computer which lattice we are talking about. So that is the problem of specifying a lattice by means of a sequence, a finite sequence of bits. And the first way of doing this is that if we have a lattice, n is typically my notation for the rank of a lattice. If we want to specify a lattice, we just assume, as on a previous sheet, that my lattice is sitting in the m-dimensional standard Euclidean space, and that I simply specify a basis of this lattice by means of the set of columns of a matrix. So I take Rm to be the standard Euclidean space. My column vectors, they are m vectors with real entries, and I just write down a set of n linearly independent such vectors, and that is the way I specify my lattice. And if it ever comes to specifying elements of lattices, because I'm going to do computations in these lattices, I simply list their coordinates. You see that I have on this transparency been a little bit ambiguous about the entries. I say real or rational, and also on the bottom line, the Rm or the Qm. What I mean by this is that for the purposes of the mathematics, I will just think and talk about real numbers. But when it comes to really phrasing algorithms and formulating theorems about algorithms, I want always to restrict to rational numbers. Otherwise, we get into the problem of how to specify real numbers with a finite number of bits. Whereas for rational numbers, I always assume that you write them as fractions of integers, and those integers you write, for example, in the binary or in the decimal system. So it is certainly an interesting question how you would round a real lattice to a rational lattice for computational purposes, and it's possible to say a lot about this, but that would be something for a third lecture, not to be given this week. Okay, so this is the first method for doing this. There is another method which is to a certain extent equivalent, but for many computational purposes nevertheless superior, and that is instead of writing down the coordinates of the elements of my lattice, all I do is that I write down the inner products of all pairs of basis vectors of my lattice. So if I have a lattice of rank n, then there's a basis of n elements. All I really need to know about the lattice, I know the group already, it will just be z to the n. All I need to know is how to take inner products of two basis vectors. Then by bilinearity I know all of the inner products of any two elements. And that matrix of inner products of basis vectors is going to be a rational matrix if I restrict to situations that I can write down completely. And it is positive definite and it is symmetric. All of those, positive definite and symmetric, all of those two properties, both of those two properties I can easily check numerically. It is an exercise for you to check. There is an efficient algorithm to test whether a matrix is symmetric. There's another efficient algorithm for testing whether it is positive definite once it is symmetric. Okay. Now you might think that this is a little bit ambiguous. If I'm going to talk about lattices, how do I really, or their elements, in this case the elements will be represented just by integer vectors, so no denominators will come up as you might have over here, or even real numbers. You might think, okay, which of the two do I really mean? So it becomes important to convert between the two methods of specifying a lattice, and to just quickly show you how this can be done. Suppose that I specify my lattice by means of a basis consisting of real or rational vectors. Then in order to get my A, I simply have to take all pairs of inner products of those vectors, which just comes down to writing down, computing the transpose of that matrix B times B. And that is my A. That is going to be positive definite symmetric n by n if B is an m by n matrix of rank n. And of course, if my B has rational entries, then my A will also have rational entries. It is a more interesting question, especially in the rational case, to go in the opposite direction. Suppose that I specify my lattice by means of this matrix, and then I know really which L I'm talking about, up to isomorphism, isometry if you like. Suppose that for some reason, for some other application, I prefer to write them like this, then it would be necessary to, given A, compute B, some matrix B that you like, satisfying the equation that BTB is equal to A. Clearly that by no means determines B uniquely, but here is a little theorem that is actually perfectly elementary, which I proved just for the purposes of giving this lecture. Namely, there is a polynomial time algorithm, and there is no doubt that it is also efficient in practice, that converts the second type of representation, the second method of specification to the first. So given a positive definite symmetric n by n matrix A, it finds in polynomial time some matrix. It is not a square matrix necessarily, that may not be possible, but it is a matrix that is small enough that you can compute it in polynomial time, an m by n matrix that represents the same lattice by means of the first method. So if you like to think about this, then an interesting special case to start from is the case that n is equal to 1. Then you have a rational, positive definite, symmetric 1 by 1 matrix, otherwise known as a positive rational number. And the question is to find a rational m by 1 matrix, an m vector in other words, with the property that its square norm is equal to the given rational number. In other words, given a rational number, you want to write it as a sum of squares. And the question is, what is the least m that you can achieve? So here I have a little question to which I do not know the answer. Namely, in general, if you know a little bit about quadratic forms, you will see that the least value of m that does it for all a's that you can think of will be n plus 3. So if n is 1, that will give 4. So that comes down to writing a rational number as a sum of 4 squares. do you know an efficient algorithm for doing this? Okay, I don't. At least not a polynomial time one. There is literature about other types of algorithms. Okay, so much then for representing lattices and their elements. So when in the sequel of this lecture and the second half of the lecture on Friday, I am talking about lattices in the context of algorithms, and I do computations with lattices and with elements in lattices, I always assume that they are represented by means of one of these two methods. And if you like, you can always go back and forth between them. Okay.
So the assumption is that M will generally be larger than N itself?
Well, we want the rank to be N. That's a theorem from linear algebra. We cannot have M less than N. You must have taught Anton too.
No, I was not sure.
Well, then you have to maybe you have to read Anton then. Okay, so here we have two questions that turn out to be important in many contexts where lattices arise. And what I would like to do today is mostly give you some illustrations of situations where you badly want to solve one of two problems. In most cases, it is a homogeneous approximation problem, and in some cases, it is the inhomogeneous approximation problem. So what is the homogeneous approximation problem? Well, you give yourself a lattice, any of my methods, and what you want is simply find the smallest possible non-zero vector. If I say small, then I mean that Q of x is small, that it is closest possible to 0. If I say smallest possible, well, that is a little bit vaguely formulated. You can interpret this in a mathematical way, namely you just want the smallest one. That is a perfectly reasonable interpretation. In an algorithmic context, however, the emphasis is on the word possible. You only want to find the smallest that you can find in the time that you have at your disposal. It may not be literally the smallest one, but it's the smallest one that you have time enough to find. And in a similar way, you have to interpret the inhomogeneous approximation problem, and that is a rounding problem. So here we are given a lattice in a Euclidean vector space E. We are given an element in E that may not be in the lattice, and we want to round it to a lattice vector that is as close to it as possible. So for example, if we take x equals 0, then an excellent answer is y equals 0. So do not think that by taking x equals 0, you have reduced you end up with a homogeneous approximation problem. They are not special cases of each other in either direction. Okay, so I would like to give you a number of situations that lead to these two types of problems, mostly to the homogeneous approximation problem. So the first example is supposed to convince you that it is reasonable to think of the homogeneous approximation problem as a higher dimensional generalization of continued fraction algorithms. So what is happening here? Well, I take my lattice to be the standard free modulo over z, z plus z, all pairs of integers. My quadratic form, the Q, is, well, it actually has a parameter. This capital N is large. What I mean by that hopefully will become clear. And then what I do is that I use this N to twist around the usual sums of squares quadratic form. And there's not a parameter, a real number, so you should think of that real number as a real number for which you perform a continued fraction approximation, a real number for which you are interested in good rational approximations. Now this substitution where I leave the y alone and the x I replace by x minus alpha y, that is a substitution of determinant 1, a linear change of coordinates. There is another substitution where I divide this one by n and I multiply the other one by n. That is also of determinant 1. We are pretty soon going to introduce a notion of a determinant of a lattice. This lattice, as it will turn out, will have determinant 1. if you have a lattice of determinant 1, then you always have, that's not a theorem we are going to see, you always have a good solution to the homogeneous approximation problem. You will have some x, and you can find such an x, of which qx is bounded by some constant that only depends on the rank. In this case, the rank is 2, it just depends on nothing. So that means that you have some good bound for this. And what does that bound mean? Well, if a sum of 2 squares is small, then each of the 2 squares will have to be small. So this y will be at most something proportional to n. So this denominator y of x over y will not be too large. There's a bound on it. And x minus alpha y, the first term, will have to be very small because it remains bounded when I multiply it by n. So x minus alpha y will really be tiny. If I divide it by y, I will make it even smaller. So you see that the difference of alpha and my rational number x over y will be very small. So I have a good rational approximation to my alpha, a small distance, and still a bounded denominator. So if you let your n range overall positive real numbers, for example, then you get a sequence of good rational approximations to alpha, and that is, for all practical purposes, the same as the sequence of continued fraction approximations to alpha. Okay, so that is the situation with continued fractions, but of course, in our case, there is no reason whatsoever to restrict to dimension 2, so here is a situation that you may view, if you like, as an exercise to extend this to higher dimensions. So now you are given not a single real number, but a sequence of real numbers, alpha 1 through alpha k, and again, what you want to do is find a simultaneous sequence of approximations with the same denominator to all of those alphas. So I like my y's to be, well, smallish, and I bound it by some parameter that will tend to infinity, and all of those differences, alpha I minus xi over y, I want those to be bounded by something much better that tends to 0 in some specified manner as my parameter tends to infinity. And then you can again figure out what sort of result you are getting once you know the theorems about homogeneous approximation, and you can find those approximations once you know their algorithms. Here is a second application which is to a certain extent dual to the first. Here we are given again a sequence of real numbers, but now we are not interested in finding rational approximations to them, but we are interested in determining whether those real numbers are linearly dependent over the rationals. So for example, if you want to know whether a number is rational, you can look whether it and 1 are linearly independent. Now, of course, there is a problem in specifying those real numbers, except if they are rational. If they are rational, they are certainly linearly dependent if n is large, so you have to be a little bit sensible about this. But what does this come down to? Well, you probably will replace them by certain good rational approximations. You take your standard n rank lattice, but the function that makes it into a lattice is now customized to your problem. Namely, first of all, you have those potential coefficients of a linear relation between the alpha I that you don't want to be too large. You want to see the small relations first. And then you put in something that is going to be tiny for a suitable choice of x's if the alphas are really linearly dependent, because if this is 0 for the true alphas, then it is supposed to be tiny for the good approximations that you have. And in order to express that you want this to be tiny, you multiply it by some capital N that is very large, and you put it as such in the quadratic form. And then what do you mean by a small non-zero vector in the lattice? Well, it means that you have a sequence of still moderately small integers for which this linear expression is incredibly small, and then you start looking for a good explanation for this. And a good explanation for elements to be linearly dependent is, for example, the following. Suppose that all my elements are the successive powers of one real number, and you somehow suspect that this real number might be algebraic. Well, if it is algebraic of some bounded degree, then the corresponding powers of my number will be linearly dependent. So you see that if you apply your lattice basis reduction algorithms in this situation to the special circumstance where the alpha I is the I minus first power of alpha, then you will get what people call an algebraicity test. What is a little more subtle in this context is that not only can you test real numbers for being algebraic or find linear dependencies with integer coefficients of given real numbers, you can actually do the same thing for p-adic numbers, even though my lattices that I defined do not live in p-adic vector spaces. So let me tell you how you can develop your abilities of defining your own lattice in order to solve these p-adic problems. So what is the situation? Well, I have p-adic numbers. P-adic numbers are given by infinite p-adic expansions. If you don't know what p-adic numbers are, I think that not so long ago someone talked about a p-adic distance, where two rational numbers are called to be close if their difference has a high power of p in the numerator. Well, if you complete the rational numbers with respect to p-adic distance, you get a field of p-adic numbers. And given a set of p-adic numbers usually means that you have some little machine that turns out as many p-adic digits of each of those alphas as you like. And then you may or may not suspect that there is a linear relation between them over the integers, and hopefully with a small height. So that means that the maximum of the absolute values of those coefficients is not too large. And the question is, how can you detect such a relation? Okay, then there are, again, two problems. The first problem is that my QP doesn't live in a real vector space, so that is problem number one. And problem number two is that I cannot work with infinite expansions in my lattice algorithms. So what do? Well, I chop off my p-adic numbers at the required precision. So if you write your p-adic numbers as infinite linear combinations of powers of p tending to infinity with coefficients that are the digits ranging from 0 up to p minus 1. I chop it off as soon as I get p to the m. So zp here is not, as in some other lectures, the integers modulo p. It is the ring of p-adic integers. Then what you will see, what you will stare at, is an element that is a rational number. Its denominator is just a power of p, and it is a good approximation to my given alpha. So alpha prime approximates alpha to a p-adic precision of, let's say, m digits to whatever side of the decimal point we are talking about here. And then what do we want? Well, we want the sum of the xi alpha I to be 0. We want a linear relation. If we chop it off at accuracy m, all we can really require is that this sum is divisible by p to the mz. You see, I made here already some partial progress because my approximations, they are lying in the rationals, even in the ring generated by 1 over p, and in particular they are sitting in the reals. And I can now look for relations that are just valid in the rational numbers, and I can look at all integer vectors that make this true. Certainly such vectors exist. There are plenty of them. I can just take, for example, for the axis vectors of which the components are divisible by very high powers of p, so that you both get your m factors that you want here, and you get rid of the denominators of the alpha primes. So that is a lattice sitting in Zn. Actually, it is sitting of finite index in Zn, and it is defined by a condition that makes it clear that I actually have a subgroup. This is a subgroup of Zn, and if I just use the usual quadratic form, then finding a short vector in this lattice is the same as finding a good non-zero a relation, linear dependency, good in the sense that the height is not too large, between my given alphas. And how good it is, whether it is good enough for you, that depends then on the application that you have in mind. Now there is one thing that I would like to comment upon given this example, namely, here I specified my lattice in a way I promised I wouldn't do it. I told you that I would specify lattices by means of a basis vector, by means of a set of basis vectors. Here I don't. I start from a lattice that is too large. I include a condition which really says that my vector should belong to the kernel of some group homomorphism, and I have implicitly described here a subgroup. So before you can apply lattice basis reduction algorithms to solve this problem, you first have to solve a linear algebra problem over the integers in order to find a basis for this group. And there exist such algorithms, but what is very entertaining about the basis reduction algorithms is that if you do it right, then the algorithm does it for you. Since here is an alternative way of doing the very same thing. So what I do is that I increase my rank by 1. So this is maybe the single situation where my rank is not called n, but n plus 1. I adjoin a 0th coordinate to the axis that I had over here, which I call x0, and that 0th coordinate is used to express the condition over here. I want that this expression is p to the m times x0. And in order to force this expression to be 0, this difference, which is what I want, I build into the quadratic form the difference of these two sides with a huge weight, capital N, which you have to pick depending on the circumstances. You have to do some computations to see how large you need n to be for the thing to work out. But what you want is that this n is so huge that if you ever run into a reasonably short vector of L with respect to this quadratic form, then that vector will really have no choice but not seeing this last coordinate at all. Because if it isn't 0, it will have to be pretty large. Why is it large? Well, this is an integer. These xi's are integers. Those alpha I primes, I know those numbers. They have bounded denominators. Let's say for convenience they are just integers as well. Well, then the whole thing is an integer. It will be at least 1. I will have a contribution n square. If I take n large enough, then that is not going to produce a very short vector of your lattice. So there you see that lattice basis reduction algorithms also help you doing relatively down-to-earth things as linear algebra over the integers. I will elaborate upon this in my lecture on Friday. So, what one can conclude from this as well is that, just as for the reals, you have also a good test to see whether a given p-adic number is algebraic and to compute its irreducible polynomial if it is. And of course I say approximately algebraic because that is, naturally speaking, all you can do. Okay. My third application of homogeneous approximation is a little bit less standard, and that refers to a situation where you already have a lattice. And let me try and explain what this is about. So I say that this is useful in integer programming. So what is integer programming? Well, you have a lattice like Zn, and you want to find a point in there or decide that none exists, sitting in a certain bounded convex domain in your Euclidean vector space. And what I have written down here is a little technique that has shown useful in this context, and that is in particular useful if you want to somehow enumerate elements in a lattice that lie in a certain bounded domain. So what am I saying here? Well, we have a lattice in a vector space. And I assume here for convenience that the rank of the lattice is the same as the dimension of the vector space. If that is not the case, simply replace the vector space by the span of the lattice. And then what I want is to find a vector in my vector space as far as possible from the origin, such that a certain inclusion is true. Now let me try and explain what this inclusion means. Maybe I should restrict to the case where my vector x that I'm talking about is not a zero vector. The zero vector actually satisfies this inclusion, but it is not going to be very long in general. So let's say that we have a vector x that is non-zero, then this Rx is the line passing through x, and its orthogonal complement, that is a certain hyperplane. Every hyperplane in my Euclidean vector space, every subspace of codimension 1, will be of this form. And if I take that hyperplane, so that is, if you take 3 space, it is just a plane passing through the origin, then the vector x will be orthogonal to it. And what I want is that this lattice is mostly sitting in that hyperplane, and those elements that are not sitting in the hyperplane, they are quite far away. So if I look at Zx, well, Z that consists of 0 and 1 and then some extensions in both directions, you have here this hyperplane, and then if you displace it by x, you get a parallel hyperplane not passing through the 0 anymore, and the distance between those two hyperplanes will be the square root of the square length of x. So what I am asking for here is to distribute the points in my lattice over a sequence of parallel hyperplanes of clearly equal successive distances, but I want those distances to be largest possible. And that is useful in integer programming, because if you know that you're only interested in lattice points that are sort of small, then you will see that you won't be able to to meet too many of those hyperplanes, and that means that for the coordinate in that x direction, there will only be a few possibilities, and if you fix the z coordinate in this representation, you will have reduced your problem to a problem that is of lower dimension, and that therefore presumably makes you happier. Okay, so that is just to explain what I mean by the problem. And to explain how you solve it by means of homogeneous approximation, well, you have to concoct a lattice, and here's the lattice that you have to concoct. It is not L itself, it is the dual of L. So here's the definition of the dual of L. Actually, I give 2 definitions. One for those of you who compute in matrix terms. And in fact, we will need the matrix description anyway if we're going to push this in a computer. So the dual of L, intuitively you can think about it as pulling L inside out. The dual of L is again a lattice. It has the same rank as L. It is the set of all vectors in my underlying Euclidean vector space, still supposed to be of the same dimension as the rank of L, all of whose inner products with my given lattice are integers. In other words, suppose that I take a basis for L, sitting in my Euclidean vector space, then I can look at the corresponding co-basis. Yeah, the ith element in the co-basis has inner product 1 with the ith element in my given basis, and inner product 0 with the others. And the co-basis of the basis of L is a basis for the dual of L. And in matrix terms, you take the inverse transpose of your matrix and you use its columns instead of the columns of the original matrix. At a certain moment, we are going to define the determinant of a lattice. The determinant of the dual will be the inverse. As I say, you always pull things inside out when you pass to the dual. And in fact, that is also something that we can do with vectors. If I take a non-zero vector in my Euclidean vector space, I can pull it inside out by dividing it by its square length. And I call it x prime. That will still span the same line. the length will be replaced by the inverse. The orthogonal complement will be unchanged, and the inner product with my original vector will be 1. So that is pulling an element inside out. Long vectors, the ones that I'm interested in here, will by this transformation be replaced by short vectors. I invert the length. From these properties, you see immediately that if you look at this set that I want my L to be contained in, that it actually consists of all elements having an integer inner product with x prime. Yeah, x prime has inner product 1 with x. It has inner product 0 with this orthogonal complement. So with an element from there, you will get inner product an integer in z. And conversely, if you have an integer inner product of y with x prime, well, then you subtract that integer times x from y, and then the inner product will be 0, it will be there. So this is perfectly elementary assertion, and that implies, if I compare it with the definition of L. Dagger, that my required inclusion, the inclusion that I want to be true for x, is simply equivalent to x prime belonging to the dual lattice. And since I mentioned already that the length was also pulled inside out, that means that my problem is just equivalent to the homogeneous approximation problem for the dual lattice. Okay, so those are a number of contexts in which the homogeneous approximation problem needs to be solved. Let me also give you just a single application of the inhomogeneous approximation problem. Let me remind you of the statement of this problem. So that is an earlier sheet that you saw already, and that is a generalization of the Euclidean algorithm to a longer sequence of numbers. And I'm talking here about the extended Euclidean algorithm. So here I'm given k integers. I want them not all to be 0, so that there is a positive greatest common divisor. And what I want is to represent their greatest common divisor as a linear combination. If k is equal to 2, then there is the so-called extended Euclidean algorithm, maybe mentioned by Jeff Shellett last Monday, and the extended Euclidean algorithm gives you not only the GCD, it also gives you such a vector, and it is actually guaranteed to give you the shortest such vector. If you want to solve a similar problem for more integers, then you have to apply inhomogeneous approximation, and one of the ways of doing it, and maybe not the most intelligent one, but here is one, is the following. First of all, I assume, and that is an assumption, if I have time next Friday, I will remove it. I assume that someone computed the GCD for me already and also came up with such a representation that he may not be happy with. Usually, when you compute the GCD, you get such a representation along with it. So let's just assume for the moment you have it, but that you think that those integers that you have gotten are not small enough for your purposes. So what do you want to do? Well, to make them shorter, you have to modify the x's by certain y's, but you don't want the d to change, so you want the y's to have inner product 0 with the a's. So what you do simply is that you look at a lattice of all the y's satisfying that linear relation. That is again a subgroup of zk. It is a lattice of rank k minus 1, because you impose one relation, a non-trivial relation, and now you want to subtract such a y from your given x in order to make the result as short as possible. In other words, the problem that you want to solve is literally equivalent to the inhomogeneous approximation problem. Okay, now let me then get started with the theory on which the algorithm will be built this coming Friday. So first of all, I announced already several times that lattices have determinants, and here I give one of the possible definitions of a determinant. I take a basis, as before. I take the matrix, which I called capital A before, the matrix of inner products. I form its determinant, which is a positive real number, and I extract its square root. Here are three other definitions that, among others, show that this is independent of choices. First of all, if you really like to work in the Rn, the same n again, the rank of the lattice, and your square invertible matrix, you just, so that is my matrix capital B, you take its determinant, but now you have to take the absolute value. What you can also do is take your Euclidean vector space, again supposed to be of the same dimension as the rank of the lattice, and mod out by the lattice. So that gives you a higher dimensional torus. It inherits a volume form from the standard volume that you have on your Euclidean space, and the volume of the whole thing, it is a compact group, will be the determinant. In other words, in planar terms, if you take a fundamental domain for L inside E, then the standard measure of the fundamental domain will be the determinant of the lattice. So that is at least base free. I wrote down another identity here, which, if you like, can serve as a definition, in fact, not just of DL, but also of the rank of a lattice. It shows that it is completely independent of any choice, and that is what occurs when you count how many x's there are in a ball of radius, the square root of R. And what you get then is the nth power of that radius divided by the determinant of the lattice multiplied by a certain non-zero expression, positive real number that depends only on n, which is supposed to stand for the volume of a unit ball. So the n over 2 factorial, if n has the bad taste of being odd, you have to replace it by the suitable special value of the gamma function. So n over 2 factorial is n over 2 times the factorial of 1 less. And if n is odd, that gets you down to a half factorial. A half factorial you can work out by using this formula for n equal 1. And it is square root pi over 2. Okay. Started 5 minutes late, right? Okay, those are going to be very useful 5 minutes. Since here we have the theorem of Minkowski, which is from the late 19th century, so to speak, the whole motivation for the whole area, which came to be called the geometry of numbers. And it gives you a bound in the homogeneous approximation problem. So it gives you a bound for the smallest x, the qx, where the minimal qx for x non-zero, only in terms of the two fundamental quantitative invariants attached to a lattice, namely its rank and its determinant. The power of the determinant that you see is 2 over the rank. That is the easy part of the theorem, because the theorem, you want it to be invariant under scaling. If you multiply all elements of L by some scalar, let's say 5, then the determinant will be multiplied by 5 to the power the dimension, 5 to the power the rank of L. And all vectors will have a square length that gets replaced by 5 square. So if you ever want this theorem to be invariant under scaling, you have to make sure that you get here an exponent 2 over the rank, because you have the square here and the nth power over there, and in this way they exactly cancel. And then there's a constant in front, which depends only on the rank. I just wrote down the rank itself here. That certainly nicely depends on itself. It is not the best possible dependency, but people know that you can at best improve this by an expression that is asymptotically constant. So I didn't bother to write down this constant. Now, what is of interest to us is that this theorem is for algorithmic purposes is completely useless. And in fact, we don't know if my L is given by means of one of the methods I explained. We don't have an algorithm that runs in polynomial time and that produces an X for us like this. And that is because the theorem of Minkowski has a non-constructive proof. And I would like to show you this proof so that you see what goes into using it for algorithmic purposes. You really have to enumerate loads of elements. So what I do here is that I assume that I'm sitting in the standard n-dimensional vector space. Let's call it Rn with the standard inner product, n being the rank. L is the number I'm talking about. That's the best value for Q of x that I can achieve. So I want to show that L is at most n times the determinant to the power 2 over n. That's what I want to show. And in order to do this, what I do is that I get myself a cube. So you take, for example, the parallelepiped spanned by the standard basis vectors, but I blow it up by a certain factor so that the diameter of the cube, so that is the length of the main diagonal of the cube, which for the ordinary unit cube is square root n, I blow it up by a factor that the diameter becomes the square root of this number L. And then you see that any two elements of C will have a distance from each other that is less than square root L. And therefore, that difference cannot be an element of L. If two elements of C would differ by an element of capital L, I would get an element of capital L with the property that its length is less than square root L, and that cannot be because the minimal squared length is equal to L itself. So this C has no two elements from the same coset of L. And therefore, if I mod it out, if I go to this torus, the map will be injective. No two elements of C will be congruent modulo L. So if I compare volumes, the volume of C will be no more than the volume of that torus, and the volume of that torus is what is by definition the determinant of the lattice. Now I can clearly compute the volume of C, since I know the volume of a unit cube, that is 1, and I know by which factor I had to blow it up, which was transforming my square root n diagonal to square root L. So that is square root L times square root n. That is the blow-up factor. I get it in n dimensions. So this is the number that should be at most dl. And if you now do some little arithmetic, then you see indeed that L is at most what I claim it to be. And you can now apply this to any of the situations that I gave you, the higher dimensional homogeneous approximation problem, and also this problem about distributing points on the lattice over parallel hyperplanes. And the result that you get here is a typical example, is that if you want to solve this problem that I told you was important in integer programming, then the best x that you can deal with, that you can find, at least in theory, the best existing x has length square, at least, again, this same constant power, constant for fixed rank, of the determinant, but now you don't multiply it by the rank, but you divide it by the rank. And to prove this, you simply combine the two last things I said, and you use the fact that is pretty clear from its definition that the determinant of the dual lattice is the inverse of the determinant of the lattice itself. As I mentioned, you pull the lattice inside out. Okay, so what I will be concerned with on Friday is the question how you do a theorem like this in a constructive way, and in particular we will see what you have to pay, how much what the function of the rank is that you will have to put there in order to do this in a completely constructive manner. And I hope to also have time on Friday to tell you about a few more applications. Okay, thank you for your attention.